Welcome back. This is the first segment for section 3.3. 3.3 really starts off in the way the textbook presents it is kind of a little bit backwards. But what I want to do first is actually draw attention to what's actually at the end of that section, which is a treatment of what's called the unit circle and the relationship between the trigonometric functions of angles related to circles in a way that's very visual. I think this is really kind of critical in terms of being able to understand the next material that comes in chapter 4, because we allude to this idea that in some sense, once you understand how the unit circle is laid out and how the trigonometric functions can be described as line segments on that circle, that now you should be able to intuit relatively quickly whether these functions are increasing or decreasing, and certain critical points as well, just based on those quantities. So let me just start by introducing this idea. I mean, it sounds really complicated, but the unit circle is not a complicated idea. Basically, we've already kind of outlined what happens with how circles are related to angles, and so the next question to ask is how are trigonometric functions related to circles? So this is section 3.3, page 1. Okay, so first, let me just make the statement that we are talking about this thing called the unit circle. So a unit circle is a circle whose center is coincident with the origin of the so-called XY plane. So a normal kind of coordinate system. You know, we're gonna, like I said, I mean, with kind of how we started with thinking of angles in space, and we sort of positioned them so the initial side is coincident with the x-axis and the terminal side is coincident with the y-axis. That's kind of the same sort of thing that we're going to do here. But let me just, oh, and I need to also mention the radius of this circle is 1 unit. Now, the unit is not specified. In fact, we don't want a unit. It's really strange to call this a unit circle and then say that it's unitless, which it is. So basically, if you think about how this circle looks on the coordinate axis, I'm actually make this fairly big because we're going to start adding some additional things to it. So if you imagine, here's the y-axis and here's the x-axis, then let's say this is 1, -1, 1, -1. It's not going to look very, I am horrible at drawing circles, but I'm going to try to put it in there. So the unit circle is in this position. And if I were really a great artist, it would look like a circle instead of a smashed basketball. So much for art school. Okay, so I want to consider, and I'm going to use a thinner pen so that you can kind of see these, but we would like to consider an angle that's superimposed on this coordinate system. So consider, let's say, an angle in quadrant 1. So, of course, in standard position, the initial ray of the angle is coincident with the x-axis, and the terminal ray determines its quadrant. So in this case, we have a quadrant 1 angle. Now we could talk about it having gone around the circle a couple times, a coterminal angle, but let's not get too crazy with this. So we're going to call this angle theta. And as you probably realize, we're going to be using radian measures for this angle. So out here on the circle is the arc length S. And notice, because this is a unit circle, the radius of any point, any place you want to talk about it is equal to 1. So I'm just going to try to put that over here. I'm going to say r equals 1, and it's no unit. So in fact, in this particular case, because theta is defined as S over R, right? It turns out that because R is equal to 1 with no units, S actually equals theta. So the arc length along the unit circle is actually equal to the measure of the angle in radians. Okay, so now let me draw some attention to some key aspects here. Now I'm going to create a couple of right triangles at key locations on the unit circle. So the first one is going to be right here. And the second one is going to be, well, maybe I need to extend this just a little bit. It's going to be coincident with this point on right where the circle crosses the x-axis in the positive quadrant in quadrant 1. Yeah. So here's something to consider. Note that this length, because it's a radius, is 1. Right? And similarly, I'm going to kind of rotate the page here a little bit. This distance is also 1. Okay? So just because those are both radii. Okay, so if we were to focus on this triangle, which maybe if I put some labels here, I'll call this O, let's call this A, B, C, and D, okay? Now, regardless of what those lengths are, let's go back to what we learned about right triangles. So if you were to use the mnemonic SOHCAHTOA, what would sine of theta be? Well, it would be, I think this pen is about dead. Let me try another one. So sine would be the opposite over the hypotenuse for a right triangle. Now note, if we're looking at triangle OAB, then this is equal to AB over OB, right? Whatever those lengths of those line segments are. But because OB is equal to 1, this is just simply equal to AB over 1, which is just AB. So note, what this has told us is that the sine of this angle is represented by the length of this line segment, right? So we could maybe even write that in there, that this length is sine of theta. And this is kind of a neat aspect of the unit circle, is that when you arrange the arrange the circle on top of the coordinate axes, and you draw your angle, that where it strikes, where the terminal ray strikes the edge of the circle, this sort of vertical line segment is actually equal to sine. kind of a neat deal. Similarly, let's talk about cosine. So cosine of the angle is equal to the adjacent over the hypotenuse. And notice again that that's going to be equal to length OA over OB. And again, OB is equal to 1. So this is just simply OA over 1, which equals OA. So cosine of theta is equal to the length of the line segment OA, which means we can just kind of put that in here. Again, the reason we're doing this is not necessarily to start defining sides of triangles or whatever else. It's because this gives us an intuition about what happens to the values of sine and cosine as an angle increases. So as an angle increases in quadrant 1, notice that sine goes from 0 to 1, but it doesn't jiggle back and forth, right? It continuously moves to higher and higher values. And so what we would say from that is, from an algebraic standpoint, the term that's used for functions that are increasing is called an increasing function. It is increasing up until you reach an angle of pi over 2 in radians, and then it starts to sort of crawl back down, okay? So that the sine becomes just the length of the pin above the x-axis. When it gets to an angle of pi, which is 180 degrees, it is now negative. The signs are actually, SIGNs are based on the quadrant, which we've already learned about. But notice it is getting larger and larger negative values, which actually is a decreasing function at that point. And then once it reaches quadrant 4, it is becoming a smaller negative number, which is the same thing as increasing. So what we can say from this, just from this sort of observation, is that sine of theta is increasing in quadrant 4 and 1 and decreasing in quadrant 1 and 2 and 3. And it actually has a point of inflection at the quadrant angles pi over 2 and 3 pi over 2. That's going to matter when we start looking at graphing these things. Now, also with cosine, note that cosine is more the x coordinate, right? So it starts out at a maximum value of 1, and then as you move through quadrant 1, its value actually decreases. So cosine is decreasing in quadrant 1. Once you get to quadrant 2, it becomes a larger negative number, because it is negative in quadrant 2, which means that it's still decreasing. Now, once you hit an angle of pi, or 180 degrees, it reverses course and starts to become a less large negative number, finally reaching a value of 0. So in quadrant 3, it's actually increasing. And then finally in quadrant 4, same sort of thing. Cosine starts out at a value of 0 at pi over 2. As the angle increases through quadrant 4, cosine increases to a maximum value of 1. So unlike sine, cosine will be decreasing in quadrant 1 and 2 and increase in quadrant 3 and 4, with a point of inflection at the quadrant angle 0 and pi. Okay, so I think I've got barely enough room to do this. So let me just point out, without all the derivation here, that this other triangle, which is OCD, right? OCD has as this sort of the side along the x-axis is a length of 1. So if we were to write tangent of theta in this big triangle is going to be opposite over adjacent. Opposite over adjacent. In this case, it's opposite over 1. which, just like we did over here, will tell you that tangent of theta is equal to the line segment CD. Remember, this requires you to have a unit circle. So if I were to sort of draw that on there, tangent of theta is this length when you have a unit circle. Now, with tangent, you have to be a little careful because the SIGNs change in different quadrants. So if you can imagine, so tangent is sort of this, I mean, and it goes at some point, it's huge in length, and in fact, it kind of blows up to infinity, which is why it's undefined. And when we talk about graphing, we'll get more into that. But for the simplistic sort of version of this, tangent, the length of tangent will have well, its magnitude will be the length of this triangle, but the SIGN might be negative. So if you're in quadrant 2 over here somewhere, then tangent would actually have a negative sign, SIGN. So since we go from positive values of tangent, where tangent increases, and then you move over into quadrant 2, where it actually has a negative SIGN, right? So it kind of comes in from negative infinity, and then as the angle comes down, the tangent value decreases, but negative, right? It's becoming less negative, which is actually increasing. And then when you move to quadrant 3, the same sort of thing happens. Now remember, again, tangent is a positive value, so it's or is non-negative in quadrant 3. So it starts off basically at the quadrant angle of pi. It starts off at 0, and then as the angle increases, it increases in a positive fashion. So again, tangent is increasing in quadrant 3. Similar sort of idea in quadrant 4, because it starts off kind of infinitely long. Once we cross 3 pi over 2, there's no way for it to really catch up there. And then it slowly moves back towards, as the angle decreases, it moves back towards a value of 0. So it's coming from a large negative value back to 0, which tells you that tangent, again, is increasing. So from this analysis of the unit circle, we see that tangent is always an increasing function. It just has some issues where it's undefined. It kind of switches from positive to negative across that boundary, but it's always an increasing function. The last trigonometric function that I want to show on this graph is actually secant. So if you extend this ray here and consider this length, so OD, remember that secant is the reciprocal of cosine, so it will actually be the adjacent, or the hypotenuse divided by the adjacent. Now for this particular triangle OCD, the hypotenuse is actually OD, and the adjacent is OC, which happens to equal 1. So by a very, very similar argument to what we've done 3 times now, secant of theta will be equal to the length of line segment OD. Okay, so that tells you, if you draw it on the picture here, that this length is secant of theta, right? So you can see from that now you have to be careful with the SIGNs, because secant is actually negative in quadrant 3 and 4, and 2 and 3, and positive in quadrant 1 and 2. So secant goes from being increasing in quadrant 4 to increasing in quadrant 1. Then, well, let's think about this. So if we start in quadrant 1, secant has a value of 1. And then as the angle goes up, secant gets longer and longer and longer and longer, and eventually kind of blows up to the point where it's undefined. So secant is increasing in quadrant 1. Now in quadrant 2, its SIGN is negative, but its length starts basically at an infinite size and slowly decreases in a negative sign until it gets back to -1 for its value. But notice that means that the function is actually increasing because it's negative sign. Its length goes from infinite to 1, but it's got a negative sign. Continuing into quadrant 3, it's now starts at a value of -1 and then just gets longer and longer and longer and longer, but in a negative fashion. So it turns out that secant is actually still decreasing in quadrant 3. Once you cross over into quadrant 4, remember the SIGN of secant is positive, and as soon as you cross over in quadrant 4, it has it starts off from basically an infinite length, and then as you move through quadrant 4, its length gets shorter and shorter and shorter till it's back to 1. So this is in fact decreasing in quadrant 4. So this is something that we will look at when we start graphing these things, which is chapter 4. But for the time being, this diagram has some pretty important use to us, and so there's going to be some problems that are related to this in the homework. I'm going to come back. I'm getting a little long on this video, so I'm going to come back with another segment where I talk about the other two trig functions. We have sine, cosine, tangent, secant. Well, there's another way to sort of interpret cotangent and cosecant in a similar way, but the graph gets too messy with all this stuff going on. So let me just pause here, and then I'll come back with another segment to talk about those other two functions, and then some not really applications, but some ways to sort of cement this idea. Okay, well, I'll see you soon.